Welcome to section 6.2, day 2, U substitution continued. So today's objective is to determine which expression to substitute when using U substitution. Yesterday you were given what to use for U substitution. Today you have to figure out what to use for U substitution. And it says in 6.2, day 1, we were told which expression to substitute with U, and now we need to decide for ourselves. So we're looking at basically as a composition of functions here, f of g of x times g prime of x dx, and we're going to get it down to the function of u du, like we were showing yesterday. You just have to figure out what your u is. So let's go through a few of these. If we have sine squared x cosine x dx, we want to see what would be the best option for using for our u. So for our u, we usually look for stuff that's got powers, something in parentheses, something that's in a denominator that will, when you take the derivative of that piece, will become the other part of the integral. So if I look at this one and I say u is sine of x, when I take the derivative of u, I get cosine x. So what I can do then is this part, this is a dx by the way, this part is right here. This part becomes u squared. So we get u squared du. And we can take the antiderivative. When we evaluate this for our indefinite integral, we add 1 to the exponent and multiply by its reciprocal, so 1/3 u cubed plus c. And then we resubstitute. Our u was sine. So we have sine cubed x, is one way to write it, plus c. So 1/3 sine cubed x plus c. And that is my evaluation of this indefinite integral. So this one, you notice we have a trig function that's raised to a power. For this one, it's easiest to make it sine x. If you did cosine x, you'd have negative sine x. You can't replace it because there's a square on the sine. That's why we picked the sine x to use. It's also raised to a power. Next one's a little trickier. We're looking at the square root of tangent x over times secant squared x. Again, we look for stuff that's in parentheses, in powers, in places like that we can replace. Well, if you look in here, we have the square root of tangent x. Well, that's sort of ugly to work with. But it's easier to work with if we replace tangent x with a u. We can do that rather easily. We have u, we're going to make into tangent x. And think about what the derivative of this. It's another thing when you're doing these. Think about how you can have one thing with a derivative equal the rest of what's left. So du, remember the derivative of tangent is secant squared x dx. So now we replace what's in the radical with u. I'm going to change to a power of 1/2. The secant squared x dx is right here. That just becomes du. And then we can evaluate. Again, when you evaluate this, you have u to 1/2, add 1 to the exponent, and multiply by its reciprocal. So 2/3 u to the 3/2 plus c. And then plug back in what we made u. So 2/3 tangent x raised to the 3/2 power plus c. And we've evaluated, and I drove right through the 3 there, but then we've evaluated this indefinite integral. We have the one in the bottom left corner. We have negative 2 sine t, and we have 4 plus cosine t on the bottom squared, dt. We have something in parentheses, we want to replace it usually. It's easier to do this if we can. And then think about if we took what's in the parentheses out, what is the derivative of 4 plus cosine t? Well, you get negative sine t, which is what's in the numerator. So let's take our u as 4 plus cosine t. The derivative of this is negative sine t. So this bottom piece right here will become u squared, because the u will replace the parentheses. But the top has a 2 in there. So we need to get this du equals negative sine t to be negative 2 sine t dt's. Almost forgot the dt there. So let's multiply by 2. So we have 2 du's equals negative 2 sine t dt's. So now this part right here replaces this part right here. What we're left with is the integral. We have to replace the negative 2 sine t dt with 2 du's. This is 1 over u squared times 2 du. I'll make this look a little better. I'll bring the 2 up front. We have the integral of u to the negative second power du. We evaluate, add 1 to the exponent and multiply by its reciprocal. This is negative 1 u to the negative 1 plus c. So when we do this, this is multiplication here. So 2 times negative 1 is negative 2. We have u to the negative first power, so I can bring that back into the denominator. 4 plus cosine t plus our constant. And that is our antiderivative. That is the evaluation of this integral. Last one we have is 6x squared minus 12x all over 2x cubed minus 6x squared dx. Let's use our denominator for our u. And we get 2x cubed minus 6x squared. du is 6x squared minus 12x dx. And you'll notice that this does match the top of our numerator. So when we do this, we get integral of 1 over u du. If you recall what the antiderivative of 1 over u du is, it's ln of u plus c. So in this case, we need the ln of 2x cubed minus 6x squared plus c. And we're going to talk more about these in the next tomorrow. When we have ln's, we do have to make sure that what we put into our function is going to work. So we can't take the ln of negative numbers or 0. So we will make sure, tomorrow I'll show you how to make sure that this stays a positive number. So here's our role reversal. Suppose you taught AP Calculus and wanted to give your class 3 hints to help them identify what u should equal when doing u substitution. What are 3 things you could say? So I would say substitute in parentheses. These are the areas we look at. Parentheses. We look for denominators. Denominator or parentheses also are going to include like radical symbols and trig arguments. What's inside a trig function? Sort of like what's inside parentheses. Those are the 3 things that we usually want to pull out if we can to make things easier. We're basically using this u substitution to help undo chain rules is what we're doing. All right, that is all for section 6.2, day 2, using u substitution, deciding what to use for our u, and then evaluating indefinite integrals. Thank you for watching and have a nice day.